Welcome to Empowered Learning. This is the final video in the video series on Introduction to Hyperbolic Functions. So in this video, we will do a few examples where we will establish the differentiation rules for some of the inverse hyperbolic functions that we've been dealing with in the past couple of videos. So the first example that I want to do is how to show that the derivative of the inverse tangent hyperbolic function is just 1 divided by 1 minus x squared, where the domain of that function are all values of x in between -1 to 1. So the first thing that we want to do is we're going to let inverse of tangent hyperbolic be equal to some other variable. So let's say, for simplicity's sake, I am going to let y equal tangent hyperbolic of x here. So if I do that, then I know if I'm following all the rules for inverses, if I take the tangent hyperbolic of both sides, then what I'll have is tangent hyperbolic of y is going to equal to, on the other side, tangent hyperbolic of tangent hyperbolic inverse. And of course, that will just simplify to x, assuming that the domain of tangent hyperbolic inverse is going to be the range for tangent hyperbolic and vice versa. So once we do that, then of course we can look at this and say that x is the same as x over 1. And so now what we're going to do to sort of get us to the next step here is we're going to borrow the whole right triangle thing to where we have the relationship between all the sides of the right triangles, like how we do for trigonometric functions. We can do something similar to that with these hyperbolic functions here. So just to kind of remind you, if we have s squared plus c squared equals 1, meaning sine squared plus cosine squared is equal to 1, then the corresponding right triangle for that would be, of course, you got, sine here, cosine down on bottom, and your hypotenuse would be 1, okay? So if we wanted to write that, this would be y squared plus x squared is equal to 1, and of course, this would be x and y accordingly, okay? So the point that I'm trying to make here is that although this relationship is not exactly the same, we could borrow this to help us get to where we need to be. And so what I want to do here is use the unit hyperbola and use this same sort of relationship here, okay? So what we could do is we could say for this right triangle here, if we let assume that x is going to act like this angle, even though it's not an angle. And we remember that cosine hyperbolic minus sine hyperbolic is equal to 1, but yet have the relationships of tangent and all this stuff be the same. We could look at this and say that, all right, we know that tangent is just opposite over adjacent. So here, let's switch this because I put x here. It's actually y, because that's the argument that's inside of there. So we do it like this. And so with this relationship here, we can figure out what this outcome is going to be here, what this hypotenuse would be. And the difference here is that now x is in the place of where s is, so that would be this. Let's see, c is in the place of 1, so we would say this. And so now, let's say if we let this side be r, then this would be r squared like that. And so now we just have 1 minus x squared is equal to r squared. And of course, to get r by itself, we can just take the square root of that. And so my point here is that we can sort of borrow this template to help us to be able to know the relationships of tangent hyperbolic sine hyperbolic, cosecant hyperbolic, so on and so forth. So we're going to make this hypotenuse look like this, okay? And so now that we have that, we can kind of use calculus at this point to be able to take the derivative of both sides of this equation here with respect to x. So if we go ahead and do that, I'm going to complete writing this here. And of course, x divided by 1 is just x. So here, if we take the derivative of the left side, since the variables do not match here, we know that we're going to have to use the chain rule, okay? And so if we take the derivative of tangent hyperbolic, that is going to be secant squared hyperbolic. But we also have to take the derivative of the inside function with respect to x. We know on the right side the variables match, so we can just take the derivative straight up, and that's just going to be 1. And so from here, if I just solve for dy over dx, then I know that this is just going to be 1 over secant hyperbolic squared of y. So now at this point, there's one or two things we could do to actually get us where we need to be as far as trying to get back to this formula here. I am going to use this right triangle thing here to actually help us out, okay? Now, we know that this is just the same as 1 over secant hyperbolic of y, that quantity there squared. So in knowing that, I could actually look at this triangle here and figure out, all right, well, what is secant hyperbolic compared to that? And we can look at it the same way as we would secant. So if we look at this like just how we would secant for a trig function, we know secant is the reciprocal of cosine. And we know cosine is according to the angle adjacent over hypotenuse, okay? So adjacent over hypotenuse is going to be this 1 over square root of 1 minus x squared. So secant is just going to be the square root of 1 over x squared, okay? So my point here is that since we can say, let me write this as cosine first. So cosine hyperbolic of y here can be looked at as 1 over square root of 1 minus x squared. This means that secant hyperbolic of y is going to look like this. And thus, if we square that, then that means that we square this, and we just get 1 over x squared. So therefore, we see that the derivative of y, and remember y is the same as the inverse of tan hyperbolic of x. That's the same as 1 over what we just found here, which is 1 over x squared. Okay? So that's how, from a formula standpoint, we would actually establish this differentiation rule. Now, as far as knowing that the domain is in between -1 and 1, the best way to do that is actually look at the logarithmic form of this particular function and figure out its domain from there. So we're going to do that next. So looking here, of course, we did the one for the inverse of tan hyperbolic. So if we're looking here, notice that it gives us all that information. But what I'm concerned about here is what's inside of the logarithms, okay? And so let me go back here for just a second. So, yep, so I use that. Okay, so I wanted to make sure that I used the right variable moving forward there. So for here, Notice that we have y's here, but I'm just going to use x's. What's important to me is to know that this term, and I'm not going to actually circle the square root part. I just want what's under the radical. This part here. Both of those expressions have to be greater than 0 in order for the inverse of tan hyperbolic to be defined. Okay, so here what I have to do is essentially solve this rational function inequality. Okay, and since I have everything in terms of x, I'm going to rewrite this with x's in it. So I have to solve this inequality here. And of course, I can either graph that inequality and see when it lies above the x-axis, or I could take a quicker way of doing this and do test intervals. Okay. Now, the main thing that I need to know here is my x-intercepts and vertical asymptotes. And so for the x-intercept, I know that my x-intercept is at -1, because that is the x value that will make my numerator go to 0. So I know that's at -1. My vertical asymptote is at the line x equals +1. So here I know that my partitions for my test intervals are going to be at -1 and +1. And I'm going to do open circles here to make sure that I know not to include those n values in my final answer. All right. So pen got stuck there for a second. All right, so now that we have this, all I need to do now is just plug in test values to see whether this is going to end up being positive or negative. So I'm going to use -2 as a test value. I'm going to use 0, and I'm going to use 2. So if I plug in a -2 in for x in the numerator and denominator, my numerator is going to be negative because 1 plus a -2 is a negative quantity. But I know that 1 minus a -2 is actually going to be a +3. So that's going to be a positive quantity. And of course, a negative divided by a positive is a negative. So the values that are less than -1 are not going to be in the domain of this function here, because of the fact that whenever I plug in negative values in for x that are less than -1, I'm going to get negative values that come out for that whole expression. So now I'll repeat the process for the other two intervals. And so I see that for the middle interval, I can use 0. And of course, if I plug in 0 in for x in both of the numerator and denominator, I'm going to get a +1, which is going to be a positive outcome. So I know all the values of x in between -1 and 1 will be values that that inverse tangent hyperbolic will be defined for. Okay. So finally, we'll do the same thing with our test value 2 here. So let's get rid of the zeros and put in the 2's. And so what we'll see here is that when we put in the 2's, the numerator will be positive, but the denominator will be negative. So we end up having a negative there. And so this shows us that the only valid x values that we have for this function are in between -1 and 1. And so that's how we would know for this answer here that x would have to be in between -1 and 1. All right, so I just wanted to do one quick example to show you how this works. If I did more examples, it would be kind of more the same thing. So once you have one down, you kind of know how to do the rest of them. It's just a matter of, again, getting that triangle together. I could have also used the identities, but to me, by setting up the triangle that way, that alleviates me from having to actually recall all those identities, but yet still get what I need to have. So hopefully this helps shed some light on this topic. And this concludes this video series on hyperbolic functions. I hope this helps to get you to understand them better. Take care.